Hi, I'm Paul Morin with the Energy Conservatory, and welcome to our webinar titled Pressure and Airflow Basics. So our agenda today, a lot of what we measure in buildings when we're diagnosing problems and taking down information is invisible. So it's oftentimes hard to really get your arms around what it is you're measuring and the building science behind it. So we're going to be covering a number of topics today to give you a better understanding of what stack effect is and how you measure that. And we'll talk about wind effect and stack effect, and wind effect go into what we're using when we take baseline readings. So we'll be talking about that and talking about how to get good readings and how to deal with wind when you're trying to measure small pressure differentials. And that's often the case when we do combustion appliance zone depressurization. When we're taking those depressurization numbers, we're often trying to measure small numbers when we might have big numbers for wind. So we'll talk about that a little bit. And we'll also get into some other building science issues that you may not deal with on a day-to-day basis, but oftentimes there are problems in a house related to airflow through a duct system. So we'll talk about pressure drops across the duct system with the air handler running and how that can help you diagnose problems in a duct system. So some other uses you may not be familiar with when you're measuring pressures in a house. And then we'll get into just some of the basic methods of measuring airflow to help you better understand how pressures relate to airflow and in different ways that airflow can be measured. So we'll start out with stack effect. Stack effect is a function of the distance from the neutral pressure plane on a building. So how tall a building is makes a difference in how far you are when you're measuring away from the neutral pressure plane, how far away you are. And so that's one part of it, and the other part is the temperature difference between inside a building and outside a building. So we'll talk about that. So it's a direct formula, can be applied, and we're showing an example here of where it's 20 degrees inside and 20 degrees outside, and we're 70 degrees inside, 20 outside, 70 inside. And we're measuring at 8 feet from the neutral pressure plane. So in this case, we'll be seeing 2.7 pascals positive at the top, air moving out at the top, and negative at the bottom, air moving in at the bottom. And if you have taller buildings, those numbers will certainly become a lot higher. So if you've got a tall building, same temperature differences, but now we're 55 feet from the neutral pressure plane, we're going to be seeing a baseline of negative 18 pascals. Another important principle to understand is when flow is Pascal's principle. Basil Pascal came up with this principle in the 1600s. So that's, when we're measuring pascals, that was named after Basil, who made some advances in pressure measurements related to fluids, and air is one of those fluids. And if we apply that to measuring airflow, it tells us that when flow is added or removed from a single zone building, the pressure in the building changes at exactly the same amount everywhere. So if we've got a single zone building, or even if you have a two-story building or a two-story building with a basement, and you have doors open between spaces, between those spaces, the entire, and you do a blow radar test, the entire building is going to change by the same amount. So this is an example of a tall building, and based on the height of our building, so we're looking at a 4-story building, and we're simulating. So we've got about a 5 Pascal temperature difference at the top and bottom. So this is assuming that the neutral pressure plane is right at the center of the building. Then you'll be seeing a +5 at the top and a -5 at the bottom. If you have a lot of, and what the neutral pressure plane is half of the air leaks are above and half of the air leaks are below. In typical houses, as we know, older buildings, a lot of the air leaks are concentrated at the top of the building. So you may have a higher pressure plane. So in other words, we'll move this neutral level up closer to the top. So we may be seeing only +2 at the top because the neutral level is higher, where half of the leaks are above that and half of the leaks are below that. That may be the case in a lot of homes with a lot of attic bypasses. You may be seeing a +2 at the top and a -8 at the bottom. So again, it's based on your distance from the neutral pressure plane on what your pressures will be. So if we apply Pascal's principle to that, when we do our blow radar test, with the blow radar, we're changing the pressure in the building by 50 Pascal. So we've entered our baseline into the gauge, so that's balanced out that -5 from where we're starting. So this is on the negative side of the scale, and this is the positive numbers on this side is 0. This darker line is 0. We're starting out at -5. We're going to change it by 55 in order to get a pressure difference caused by the fan of 50. So we're seeing, so we're actually at -55 at the bottom of the building. At the top of the building, we started out at +5. So this is our 0. We started out at +5. So we're moving 55 or 50 Pascals, and so we've got a change here between these two numbers of 50 Pascals at the top. So if we stick a probe out of the building at the bottom, we're going to be measuring -55. If we stick a probe up through the roof to measure up there, if we're able to measure right at the top of the building to the outside, we're going to be measuring -45 Pascals. And this, I think this, I kind of like this graph from a tech log file. This is a baseline period of record. So along the bottom, this is graphing pressures over about a 2-minute period. So on the time scale on our x-axis, we're at about 2 minutes. And this was an 11-story building where we did some repeatability testing, and we're seeing graphs of pressures where there's 4 green pressures down here, 1 on each side of the building, the 4 sides, and we also measured pressure at 4 sides at the top of the building, so on the roof. We put the pressure tubes just over the edge of the 4 sides up on top. And the reason we're seeing a variation between these pairs of readings is this building sloped pretty steeply down a hill, and it was long in that direction. The building is really long in that direction, and so 2 of these bottom 2 are going out at the bottom level of the building, and these other 2 are going up about 2.5 to 3 stories higher is where these other two went up. So and then these are at the top. So if I add the building to this, we're seeing an 11-story building. We're seeing these pressures are at the bottom of the building. These pressures are up a couple of stories, and these pressures are at the top. And we can see from where and assuming that all of these pressures are evenly spaced along floors, our neutral pressure plane, or where we'd be measuring 0, is right near the top, and we're only at about positive 4 or 5 pascals at the top, and here's negative 20 at the bottom. This was about a 30-degree day with an 11-story building, so we're seeing pressures of 18, 19 at this location, and 22, 23 down here. Much higher pressures at the bottom of the building. So what we can kind of think of the building science behind it is that atmospheric pressure is about 30 inches of mercury or so, normal at sea level and 68 degrees, and that amounts to about 3 pascals per foot. So we're not seeing that with a pressure differential gauge. We'd see that with a barometer, but we're not seeing it with a pressure differential gauge. So what we can think of is colder air on the outside of the building is heavier. So it has a weight. Just like if you think of going underwater, you've got the weight of that water above you. The deeper you go, the more weight of water you have. The same is true with the atmosphere. The closer you are to Earth, the more weight of air you have. The farther you go up, the less weight of air. And we've got colder air outside than inside, so that weight of that air is pushing down harder at the bottom of the building than it is at the top, and it's forcing air into the building. And the farther you go up the building, it'll force air in less. And remember, air out has to equal air in, so it's pushing air in at the bottom, it's pushing air out at the top. And the way you measure that, what number you'll be measuring on this building depends on where you stick the probe out. If you stick it out at the bottom, you'll be measuring that pressure. If you drag a hose all the way upstairs and you've got the gauge up here, you've got that tube going all the way down and then out, that doesn't change the pressure measurement. The pressure measurement is dependent on where you go out from the building. In fact, if you have a gauge at the bottom of the building, run a tube all the way up to the top and hold it up at the ceiling here, you'll be measuring 0 pressure. Pressure in the building is all the same because the temperature is the same. You won't find a pressure difference within the building if all the air handlers are turned off, all the mechanical systems are turned off, and you've got single zone conditions. You're going to see the same pressure within the building. If you want to measure the stack effect pressure, you need to measure, that's dependent on where you stick the probe out. If you stick it out at this location on a calm day, you'll measure 0. You're at about the neutral level, and positive numbers above that, negative numbers below that. So hopefully that kind of helps you understand that basic building principle of stack effect and what that is and how you measure it. Wind effect, we're all aware of how wind will affect our numbers on a windy day, and you'll get different variations of wind depending on where you measure the pressure. So we can see on our windward side, we've got kind of eddies on both sides, on the windward side and the leeward side, and we'll get wind variations on both of those sides. And basically, the air is going to be moving the least on the leeward side of the house close to the house is kind of a dead spot where you should see a fairly calm area. So, you know, both pressures inside and outside the house are changing, and you can't change that. People try lots of things to change that, but they don't have a lot of effect. And one common one is to put the end of the tube in a pop bottle. And you know, I've seen variations on how that's done. I've had people call where it's a quality control person, and the person has the cap on the bottle, and they drilled a hole in the cap and they put the tube in there. Well, that's what you're measuring in that case is house with respect to bottle and not house with respect outside. And if the sun is shining on that bottle, your pressures are going to be expanding in the bottle, and you're not going to be reading an accurate reference. So and if the wind is blowing into that bottle, or you're going to get pressures inside that bottle that are different than what it is outside. And if the wind is blowing across the end of that bottle, you'll get some Venturi effect, and it'll change the pressure. So it is a good strategy to protect the end of that tube from rain, but doesn't necessarily help you when it comes to evening out the pressure variance you see from outdoors. I've heard of people putting it in a sponge, and there are some other commercially available pressure measuring devices that are sold for commercial buildings and other uses. And I've heard that, you know, using an inverted pie plate that's up on legs helps some pressures. And Gary Nelson at our office has done really extensive research on finding out what the best method is to calm all of these things, where he's recorded pressures over long periods of time to try to determine what's the best. And generally speaking, putting the tube on the leeward side of the house, the side away from the wind, is going to be your best option in most cases. If you're taking measurements in the city where buildings are fairly close together, and you know, maybe they're only 10 or 15 or even 20 feet apart, buildings, and the building next to you is taller than the building you're in, then you can get some other turbulence between the houses, and the leeward side may not be the best location. And in cases like that, I would throw it out in the front yard in long grass, or in you know, if you can get it in some bushes or something, that may be your best location. So playing around in certain conditions where there's things around inside the building that can be causing it, the leeward side may not be the best, but generally speaking, in most cases, that's going to be your best location. And having it towards the middle of the building, up close to the building. On rainy days, I'd recommend, like we're doing here, where we're taping it to the side of the building, if the tape will stick to the siding you have, and pointing the tube down, so rain won't get in that tip, is helpful also. So this is another baseline period of record from another test that was done, and you can see kind of the variance. Again, this is a tall building, so we're seeing pressures anywhere on this scale from -5 pascals down to -25. So our pressures are kind of all over the place, and they're varying by quite a bit. You know, the variance is somewhere around 5 pascals in the measurements, and even more. And you can see the green one here that's pretty calm is on the leeward side. So you can see you can get you know, more stable. Wind gusts aren't having as big of an effect But windy days can be tricky, and leeward side in this case was the best of the four to be measuring. So stack effect plus wind effect are the things that affect our baseline readings, and it's important to take baseline readings, and we'll go over some reasons why in this case. So to get the best readings, we recommend putting it on the leeward side of the house. Using time averaging certainly helps, and helps you get more stable readings. And on windy days, using software is always a way to get better readings. Either if you're doing a blower dart test, use Tektite. If you're measuring combustion appliance zone readings, we've got a software called Techlog 3, and both of those all of our software are free downloads from our website. And then you can graph those pressures like we saw in those previous slides. You can graph those pressures and get an idea of how windy it is, and see if turning on the kitchen fan, if you can even tell how much the pressure changed due to that kitchen fan or clothes dryer or bath fan. It gives you a better sense of and better confidence in your numbers. And sometimes on extremely windy days, it's not even worth it's worth documenting what pressures you're measuring, but trying to make sense of it is just not possible. You're trying to measure 2 pascals when the wind variation is 5. So we'll talk a little bit about why it's important. So understanding some of the principles of baseline readings for blower dart test zonal pressure numbers or CAZ numbers. When you're taking attic pressure tests, a lot of you are required in your programs to take zonal readings to the attic or other zones when you're doing a blower dart test. And remember, what we talked about with stack effect. If you're taking a blower dart reading without baselining it, you could be getting faulty numbers, because that when at the bottom of the house you're at -55, when the blower dart is running at the top, you're only going to be reading -45 if you measure directly to the attic or directly to the outside. You started out at +5 and you're ending up at -45. So when you're measuring 45, you're actually measuring a change of 50, and you've done a perfect job of air sealing, and it looks like you've still got room to play with. So we'll go over that in a little more detail, because it's kind of hard to wrap your arms around that concept. So let's use an example where you've got a really well-sealed attic. So it's almost perfectly air sealed, and you've got big attic vents. So measuring your pressure to the attic is just like measuring it to the outside at that location. And I'm using that example in this case so you can kind of, I think it'll give you a better understanding of what you're measuring in this case. So we're going to start out, we're running our tube outside where we would for our blower dart test. We're turning the gauge on, and we're reading our pressure at the bottom, and it's kind of hard to see the number on the gauge here, but we're at a -5. So like that example we used before, we're at -5 at the bottom of the building. And if we put our tube out in the middle of this building, in this case we're at 0. So we're assuming that the neutral pressure plane again is right in the middle of the house. And if we put it at the top of the house, now we're reading a +5. So if we go into the attic, in this case, we're also getting a +5. So we're reading +5 if we take our baseline reading to the attic. So if we, like I mentioned before, if we measure from from the floor of this bottom level of this house up to the ceiling on the top level, we're going to be reading 0. And the reason for that is, remember we talked about the weight of the air is what's causing our pressure readings. Well, the weight of the air inside the tube is the same as the weight of the air outside the tube in this case. And so that tube might as well be invisible as far as reading pressures goes. You can play around with this and try it if you don't believe me. Leave your tube on the floor and put your gauge up at the ceiling on the second floor, and you'll be reading 0 pressure. So now we're turning on our blower door. So we're changing the pressure by 50 pascals. So if we're not using the baseline function of the gauge, the baseline will zero out this -5, and we'll see a change caused by the blower door fan of 50. But we're going to see we'll actually be changing our pressure. If we measured it at the bottom of the building, when we've changed it by 50, will actually be -55. So then, if you're using 2 gauges, you'll bring your second gauge up into the attic, and the house is changed by 50, but we'll only be reading 45 pascals, because the difference between +5 where we started out and -45, it's changed by 50. We'll be reading -45 in the attic, where if we measured this baseline to the attic to start with, then our reading would be 50. Our change in pressure caused by the fan is 50 pascals, and we've done a perfect job of air sealing in this case, or at least we'll be getting the right number to put on our forms, because we're looking for the change in pressure caused by the blower door fan. What could even make this number look worse is if we baselined our gauge at -5 and then measured our pressure in the attic. The difference between -5 and -45, if we baselined it at the bottom of the house and then measured at the top of the house, our difference between -5 and -45 is only -40. So we'd be getting an attic reading of 40, which would look terrible, when actually we did a perfect job of air sealing. So I hope this isn't too confusing, but you can watch this maybe a second time, and that may give you a clarification, or you can give me a call and I can help talk you through it. But it is really important to understand these building science basics when you're measuring attic pressures, so you're getting the right numbers. If you have a second gauge, baseline that gauge before you do your blower door test with the tube going into the attic, and then do your blower door like you always do with the blower door reading baseline. Then you'll be getting the right numbers. With CAZ pressurization, depressurization, the combustion appliance zone, you've got your gauge down the combustion appliance zone. What I would recommend is for your baseline, set your DG700, set your gauge to 5-second averaging, and write down 5 numbers, 5-second averages. It'll blink with a new number every 5 seconds. And that gives you an idea of what the variance in those numbers are. And if the difference between the highest number and the lowest number is 5 pascals, you've got a pretty windy day, and it's going to be hard to read 2 pascals where you have a variance of 5 between your numbers. And you can't really, this is just 5-second averages. It takes 30 seconds to write those numbers down, so it doesn't take much time, and you're getting a snapshot over those 30 seconds. And you remember in some of those previous things, it may be calm. You may be measuring those during kind of a calm period, and you may get some gusts. So it's not giving you a totally accurate, necessarily an accurate baseline reading. One of those 5 might not be even accurate, but it gives you a snapshot over time of how much variance there is on that given day. And the distance between the highest and the lowest numbers gives you an indication of how windy it is. And do the same when you do a worst case. So write down 5 5-second averages, or maybe you want to set it to 10-second average, and write down 5 10-second averages for your baseline and 5 10-second averages for your worst case. And that gives you, pretty good indication if you're able to get good numbers. If those numbers are real stable, you've got some confidence in your numbers. If they're not stable at all, you may not be able to make sense of it at all. And you have to accept that some days it's just going to be too windy to get meaningful numbers. You can try using TechLog and graphing them to get better data, but even doing that, some days will just be too windy to get meaningful numbers. Next, we're going to take some pressure measurements to help troubleshoot problems with airflow in an air handler system. So we'll take our DG700 and we'll use a static pressure probe. Those of you who have duct blaster systems are familiar with static pressure probes, and some of you may be using it to measure draft, measure the static pressure in the water heater vent connector. But in this case, we're using it to measure the pressure in an air handler system to help troubleshoot the problem. So the first measurement we're going to take is, so you can see we've got a little icon of a static pressure static pressure probe here, and we're putting it in the return duct, and we're actually I put the gauge out here so it could be bigger and we could read the numbers, but actually the DG700 is going to be in the house. So we're measuring the pressure across the return grill here. It says filter grill, but in this case we're going to put the filter in a slot here. So we're measuring the pressure across the grill here. So turn on our gauge, turn on the air handler, and we're seeing -8. So we're seeing a pressure drop across that grill of -8. So that gives us an idea how restrictive that grill is. So I'll put a -8 here for the pressure drop across that location. Next, we'll connect another tube and measure the pressure at the end of the return duct system. So we've got some resistance added by a couple of turns here and by a length of return duct, and we're measuring a -28 the pressure difference between the duct and the house. -28 at this location. So if we look at the so now we'll move our tube, so we're measuring the pressure difference between these two locations. So we're getting the pressure drop caused by those elbows and that length of return duct, and that's -20. So we've got a delta P change in pressure from these two locations of -20. So that's our pressure drop caused by the elbows and the length of return here. So we've got -8 change in pressure across the return grill, and we've got 20 pascals between those two lengths of ductwork. Next, we'll take it above the filter. So now we're going to look at what's the pressure drop, what's the total resistance to flow at this location, and that's -48. So -48 is our pressure measurement at this location, and if we look at the pressure drop across the furnace filter, we're seeing -20. So a change in pressure of -20 across the filter. And typical pressure drops across filters can be anywhere from 20 to 100 pascals. So 20 seems like a big number, but actually it's pretty small. Pleated filters are going to have if they're a thin pleated filter, a 1-inch pleated filter, they're going to have a lot of resistance. If you have a wider one, you know, 3 or 4 inch wide pleated filter, they're going to have a lot less resistance. And dirty filters will definitely have higher pressures, and as you have a higher velocity, you'll have a higher pressure drop across that same filter. So, you know, oftentimes on filters, you'll see that it'll be labeled on the filter that it'll, you know, what kind of pressure drop you can expect. But if you've got a higher velocity in the system, you could have much higher pressure drops than what that filter might be rated for. So keep that in mind. So you know, our air handler cabinet is here, so our total resistance on the return side is -48. So we add up all the pressure drops across that system. We're starting at 0 in the room, going to -8, and so on. All those are additive and add up to -48 is our back pressure on the return side. All right, and then next we're measuring the pressure on the supply side. So we're seeing a positive 97 on the supply side here. So if we do this is referred to as an external static pressure, and that's essentially the pressure across the air handler fan. So we're on the fan side of the filter, and we're on the fan side of the air conditioning coil, and we're measuring a total external static pressure of 145. So the pressure difference between a -48 and a positive 97 is going to be 145. So you can think of this on a number line. If you imagine a number line where you've got 0 and positive 97 on one side and -48 on the other side, 145 is how far you have to go to get from the -48 all the way up to the positive 97. So difference between those two, 97 minus a -48, minus a negative is a positive. Remember that from back in math class. So that's how we arrive at that 145 for our external static pressure. And a lot of air handlers will have about a 0.5 inches of water column for a maximum external static pressure, and that number will be on the nameplate. Typically, where it has the BTU output and input, and the model number and serial number and those kinds of things. 0.7 is becoming more common with air handlers now, but you'll see a lot of them at 0.5. That'd be 125 pascals. So if this system had a maximum external static pressure of 0.5, which is equal to 125 pascals, this would exceed that, and you'd have to look for areas where you could make that number better. And sometimes you have to redo the duct work and add more supplies or make it bigger to help relieve the pressure in that side of the system. But for now, we're just kind of troubleshooting to see where the biggest numbers are. So the next pressure we'll measure is above the air conditioner coil, and we're getting 40 pascals there. So 40 pascals at that location. So the pressure difference across that air conditioner coil we're seeing is -57. So we have a -57 drop in pressure across that coil. So again, that adds resistance, so the pressure goes lower. So typical what we'll see across coil is somewhere between 25 and 100 pascals. If it's greater than 75 pascals, we'll want to inspect that coil and see if we can't clean it up and reduce that resistance, get all that gunk out of there that's accumulated over the years, and so we can get more airflow across that. Now we're measuring in the supply trunk, and we're measuring a +20 So our pressure difference between those two locations, right above the coil and then in the supply, is pressure difference at 20. So now we can see, we can get an idea where our biggest pressures are and where we might be able to make some improvements based on these numbers that we've gotten. Next, we'll be talking about some of the basic building science again, different methodologies in science behind measuring airflow. So one method is the time it takes to inflate a known volume, and this is typically done with a stopwatch and a paper bag. And we can see this information was garnered from a presentation that Bruce Manclark did. So this shows the formula and a chart showing the methods. The Canadians were the first ones that I knew of that came up with this method quite a while ago. And you know, it costs you $1. You've got a 55-gallon or a 33-gallon trash bag, and it's attached to a hanger, and you put it over the register and count how many seconds it takes to fill up. Or if you're measuring a return, you get the bag full of air, put it over the register, and count how much time it takes to deflate. So in this case, it gives you an example. You're filling in the numbers here where you filled in 55 for the gallons number and 4 for the seconds it takes to fill the bag up. So in this case, it's 55 times 0.0156 times 60, and divide that number by 4, and you get 129 CFM. And 129, it sounds like you're accurately measuring it to 129. I would think of this more as, is it 30, 60, or 90, or something on that order. If it's we can see it's about 5 seconds gives us 50. 100, if we're at about 3 seconds, we're at about 100, and if we're at 2 seconds, we're at about 150. So that's more like it. Is it 50? Is it 100? Is it 150? And the difference between with a 33-gallon bag, the difference between 50 and 100 is only 1 second. So it gives you a ballpark number, and maybe that's all you need. Is it 50? Is it 100? Is it 150? And this method will tell you that. The next method of measuring airflow that's used is measuring the airflow through an orifice, so through a hole. And this equation is for measuring airflow through what's called a sharp-sided orifice. So if you have a round hole or a square hole in a thin plate material, you can if you're able to get stable readings on both sides of that hole, that orifice, you can use this formula and figure out what the airflow is. So this is 1.07 times the area of the hole in square inches times the square root of the change in pressure in pascals, and that will give you CFM of flow. The exhaust fan flow meter uses this methodology. It's calibrated, so it's not exactly the square inch of the area and the square root of the pressure, because there is some leakage around the hole here and the door itself. So this is calibrated to give you a little more accurate reading, and it's got a gasketed box to make a tighter seal so you can get some accurate readings. Before this was developed, the company I worked for, we just used a cardboard box with a hole in it to start out with, and then we started using a tub for files with a hole cut in it, and then eventually we moved on to this, and it was much more accurate. But this is using the flow through an orifice equation, and that's what blower doors use also. Is you've got a flow sensor that's back behind the ring, and you're measuring it with reference to the room, the space you're in. So the pressure across that flow sensor is what you're measuring, and this isn't strictly an orifice. It's more of a nozzle shape, so the formula is slightly different, but that's the basic principle. Is in some standards this is referred to as an orifice blower door, and that's what basically what we're doing, what's being applied in those cases. Our duct calibration plate, if you're not familiar with that, it's a plate you can purchase to put on the end. You tape it to your square transition, stretch out the flex all the way, set up in the depressurization mode, put your pressure tap, so you're measuring the pressure in the duct, the flex duct at this location, and measuring the airflow at 25 pascals, and it should be, I think it's between 106 and 109 CFM for your system to be within calibration. So it doesn't tell you if your gauge is within calibration or your fan is, but those two working as a system are within the calibration specs. So flow through an orifice again. Another method of measuring airflow is velocity times the area. So you'll have to accurately measure the velocity and accurately measure the area. And that's not done by using a static pressure probe. It's done, static pressure probe measures static pressure, not velocity pressure. So we need to use a pitot tube, and you need to use that in a duct. Pitot tube is measuring two different pressures, static pressure and total pressure. So static pressure is like with static pressure probe, you have small holes on the outside of the tube and a sealed end. So this is measuring, it's a tube within a tube, so it has a sealed end on it, and it's measuring holes through that static pressure through these holes on the outside of this tube, and that goes out to this one. So you connect this tube to get your static pressure, and then total pressure goes through the center of the tube, and so you're measuring total pressure at that space, and you connect both of these to the same side of the DG700 and set it in the PRV mode. So you're connecting these on channel B, two tubes, both tubes on channel B, one to the input and one to the reference. Difference between those two is velocity pressure. And then the DG700 will convert that velocity pressure to velocity in feet per minute. And you need to take that measurement at multiple locations. And when you buy that static pressure probe, it'll typically give you these, or on the Dwyer website it gives you these charts and tells you how many pressures you need to measure, because you'll get very different pressure at the edge of the duct than you will at the center. So as you take it at multiple locations, and as you can see, you need to measure it in two locations at 90 degrees to each other, and you also need so many duct diameters of tubing to measure it. So this needs to be rigid duct. In flex duct, it's going to be too turbulent to get accurate measurements, so you need rigid duct. And for example, if you've got a 6-inch duct, you need 10 feet of space, 10 feet of length of that duct to get a measurement. And you need to be so many diameters from a downstream elbow and so many diameters from an upstream elbow. So you'd need 10 feet of straight duct. So this isn't very practical or very accurate, and it's very time consuming to get good measurements. So not necessarily a method that anybody's doing. It does work well if we used to do this when we're measuring airflow in big commercial buildings, and you've got a duct that's 4 feet by 12 feet wide, and you've got 40 feet of straight duct. You can get very accurate readings. You know, you have a pitot tube that's 4 feet long, and you can get very accurate readings of airflow by measuring at all those locations and averaging them. So the velocity you're given is in feet per minute, and you multiply that by the square foot of the area of the duct. Feet times square feet is cubic feet, so that gives you cubic feet per minute. So you need to accurately measure the velocity, and you'd average all those numbers and accurately measure the square feet of the duct, and that'll give you cubic feet per minute. This is the principle behind the TrueFlow air handler flow meter. You get 2 plates for that, a 14 by 20 and a 20 by 20, and that's what this is doing. It's measuring those multiple readings you need to take of both velocity and static pressure, and it averages all of those readings at the same time. So you're getting accurate readings of measuring those all at the same time, and gives you a quick, easy way of measuring the total airflow through an air handler system by putting this flow grid in place of a furnace filter. So now we'll take time to answer questions. Thanks for attending the webinar, and we'll review those questions, and feel free to type in more questions as we're going along, and we'll review the questions that have been asked so far, and if you think of other questions, feel free to type them in. And we're looking for feedback on what you'd like to see in future webinars also. We do have some time to take questions. You'll notice that we've been answering some questions as we've been going along, so you can look up there and check out some of those responses, and we'll review some of those questions that have been asked so far. And also, we'd like you to take time. You may have noticed on the right there, we've got a future webinar and speaker survey, and we'd appreciate if you take time to give us some feedback on what type of webinars you'd like to see in the future. In fact, this particular webinar was based on a recommendation from one of our customers. So thanks for that feedback, and we'd like some feedback on this webinar too. I know this was titled a basic pressure and flow webinar, but we did get into quite a bit of detail. A lot of what we do when we're diagnosing problems in homes has to do with pressure and flow, and a lot of the building science of diagnostics is related to pressure and flow. So this webinar was about some basic building science principles, but give us some feedback if you thought this was too advanced or too simple. That's feedback we're always looking for. So some of the things that were asked so far is, one good question was, how do you determine, if you want to know where the neutral pressure level is, neutral pressure plane in the building where half the leaks are above and below, how would you do that? First of all, it would need to be a pretty calm day for you to be able to find that. I did experience being able to find it real clearly one time when we're doing diagnostics on a cabin in northern Wisconsin when it was below zero, and it had tongue and groove paneling with no air barrier or vapor barrier behind the tongue and groove paneling, and and it was a really calm day. And you could see with an infrared camera right where the neutral pressure plane was, because you could see the cold air coming in below one point and the cold air going out above that point through the leaks in the tongue and groove paneling. So you could see, it was a vaulted area, and you could see really clearly up 2 stories and see right where the neutral pressure plane was. You're not going to run across that probably ever to see something like that. But what you would have to do is drill a bunch of holes through the house and stick a probe out in different locations until you get to 0. So it's really not practical. It can be helpful if you can measure, at the top of a building, maybe out through, if you can snake a rigid tube out through the top of a window on the upper floor, and then out through maybe a basement window, or if it's a walkout through the bottom of a basement door, you can get an idea what the pressure is at the top of the building and what the pressure is at the bottom of the building on a calm day, and get an idea of where the most of your leaks are. If you've got a low number at the top, then your neutral pressure plane is high. Your 0 is high. Remember that graph we had where we had a high, we had readings of 5 at the positive 5 at the top and negative 20 at the bottom. That had a high neutral pressure plane. A lot of leaks at the top of the building, and the pressure was low because that 0 pressure was up high. And then positive above 0 and negative below 0. So you can get an idea of where the biggest leaks are in a building by comparing the pressure at the top to the pressure at the bottom. So that it does have some uses. Does that change in pressure at the top, your pressures at the top of the building, your pressures at the bottom of the building, does that give you an idea how leaky the building is? And the answer to that is no. Leakiness of the building has no effect on stack. Stack is just a function of the height of the building and the temperature difference between indoors and outdoors. Does the neutral pressure plane change depending on environmental factors like wind, temperature and wind? Certainly temperature affects it, and wind will also affect it. It doesn't affect the neutral pressure plane, but I shouldn't say that. It does affect neutral pressure plane. It won't affect stack effect, but it does affect where air is leaking into a building and where air is leaking out of a building. If you've got a 30-mile-an-hour wind, that's going to override stack, and you're going to have all the air coming in on one side of the building and all the air going out on the other, rather than coming in low and going out high. And wind can, both wind and stack together will determine where air is leaking and where air is leaking out. Time average. There's quite a few comments about time averaging. Time averaging on windy days is a great idea. It's something you should all be doing. If you're taking your, essentially what you're doing when you're taking a baseline reading is you're taking a time average, and hopefully you're watching that time and seconds count up on channel B, and then when the number on channel A is starting to stabilize, then you're entering that. So essentially you're entering a long-term average into your baseline reading. And you'll also want to do that for your CFM at 50 reading. If you take a 30-second baseline, you should be taking a 30-second Florida reading at 50 Pascal. So change switch that to time averaging and do that. And also with CAZ testing, it's a good idea to take 5-second or 10-second or long-term average readings to get a better idea of what your baseline readings is. And if if you're doing that in stages, which is helpful if you're trying to diagnose what's causing the biggest problem, is it the clothes dryer, is it the kitchen fan, or is it the air handler? And you're taking readings and writing them down at different points in the test, you want to make sure and clear the time average between your readings. And you'll do that. The clear button doesn't work for that. It'll just beep at you if you hit the clear button. The way you clear time average is to put it back to 1 second. So if you're at long-term average, you'll put it back to 1 second and then put it back to long-term again. So that's kind of some things to keep in mind when doing time averaging. Let's see, I think we've got a few more questions that are coming up here. So the survey, it says on the right side, it says future webinar and speaker, future webinar. So there's a survey, and click the Browse To tab. You'll see a Browse To tab there, and then it'll let you take that survey. Let's see. Does the neutral pressure plane change between full basements and walkout basements? And the answer is no. Leakiness of the building doesn't affect baseline. It's only the height of the building and the distance from the neutral pressure plane. With a full basement, it's hard to get the pressure at the bottom, at the bottom of the house, because you'd have to drill a hole through the concrete block and stick it out at that location. So it's not practical to be measuring pressure with reference outside in full basements. So if you're trying to measure the neutral pressure plane, that's not really going to be possible in a full basement. But it should be possible with a walkout. So in that respect, your ability to measure is definitely different. Proper way to measure draft in a double wall pipe. Some water heaters, you will see double wall pipes, and I would recommend probably not drilling holes in double wall pipes. What I've seen some people do is they'll have a screw, like a stainless steel screw, or something that won't rust, that is the same diameter as the hole you drill, and you screw that in there and leave it in. That's one option if you need to be measuring draft. I think a lot of programs have gone away from measuring draft and instead are measuring depressurization numbers, how much the house is depressurized, rather than measuring draft and testing for spillage. Spillage is really the bottom line. It's more important to check for spillage than measuring draft, in my opinion. But if your program requires you to measure draft, then you do need to measure draft, and maybe ask your program what they recommend for if you should be drilling those pipes. Can you review baseline again pertaining to blower door tests? The DG700 is, if you're using the baseline function on the DG700, that zeroes out your gauge. So if you have a calm day and you turn your gauge on and you're reading the temperature difference between inside and outside at -5, which isn't unusual in Minneapolis in the winter. You've got a baseline of -5 on a perfectly calm day, and you enter that baseline into your gauge is going to be reading 0 now. So it zeroes out that baseline reading. So what it's displaying now is not the actual pressure between inside and outside as you turn the blower on. It's recording the change in pressure caused by the blower fan, which is what you're interested in. That's usually referred to as the induced pressure, the change in pressure caused by the blower fan. So you're zeroing out the baseline by entering the baseline into the gauge, and now what's being displayed is a change in pressure caused by the fan. Okay, let's see. We have lots of questions here. Okay. I didn't go into a lot of detail on calculating I guess Mike's question has to do with, can you use the orifice equation when you're measuring a branch duct out of a system? And the answer to that is no, because there's not, you can't, you can use the flow through an orifice equation if you can accurately measure the pressure on both sides of the orifice. And in a branch duct, that's really, depending on where you measure it, you're going to get much different readings in that duct. If you measure close to the duct, you're going to get a way different reading than what you're going to get in the middle of the duct. So it's hard to get a representative static pressure in that case. So that's not really an option that's not a good application for flow through an orifice when we're talking about a branch duct. Do you need 2 DG700s to measure zonal pressures in a house? And the answer is no, but it certainly is helpful. You need to, all of your zonal pressure should be baseline adjusted. So if you're measuring a zonal to the attic, it's helpful to be able to use the baseline function of the gauge the same way you do on the blower door, and that will give you much more easy to understand numbers. Okay. Put them on a CFM air leakage. Does stack effect normally create in an average house? The air leakage is a function of both pressure and the size of the hole. So you will have more air leakage in a leakier house because you have more holes. So there really wouldn't be an average amount because there are so many variables. If you think of measuring pressures across every hole in your house, it's really a function of what's the pressure across each of those holes at that given time. And in a windy, gusty days, your pressures are going to be changing everywhere all the time, constantly. So it's really hard to get a feel for how much air is leaking out of a home in real time, or how many CFMs there would be that way. It certainly gets real complicated really quickly. Okay, so I think that's about it. I think I've covered gone through all of the questions, and we had a lot of good questions today, a lot of questions in general. And if you've stuck around this long, thanks for doing that. And feel free to email me or give me a call if you have any further questions if something wasn't clear. So thanks for attending our webinar, and we appreciate any feedback and suggestions you can provide. Thanks.